Okay, so without further ado, let's move on to the content of this lecture. So today we will start talking about. Actually, I'm gonna use this. Okay, so we'll start with differential operators. So let E and F be vector bundles as before on a manifold with boundary. And so, oh, I'm sorry, I forgot to switch. Sorry about that. I forgot to switch. Okay, so let's start again. So we're going to talk about differential operators. So let E and F be vector bundles over M. And so D is a differential operator. So this is just a map from the smooth functions of E, and it lands us in the smooth functions of F. And for us, differential operators are always linear. Okay? So I want to define what it means for a differential operator to be of order n. So we say that D is at most don't we have a caption? What? I have differential operators up top. Yes. Okay, so D is at most order M if in every chart trivialization. So whenever I'm typically talking about charts and trivialization, it just means that I've taken the charts and the trivializations to match up to each other. Okay? Let's say U psi with frames E beta and F theta for E restricted to U and F restricted to U respectively. There exists smooth functions X maps to A alpha theta beta X. So we're indexing over alpha, theta, and beta such that we can write the operator D U inside this open set U at X as equal to, so here this is a multi-index, A alpha theta beta X okay, so I think I have that written up right. So where alpha is alpha 1 up to alpha n. So this is, and then the modulus alpha here I'm just writing as the sum. Okay. So this is just really formalizing what we expect a differential operator to be on a vector bundle. Okay, so there's nothing really magical happening here. So let's define diff MEF to be the set of such operators. At most order M. So it's clear, of course, that a differential operator of at most order M is also a differential operator. So I should say that this is the end of the definition here. Well, okay, we can organize. Yeah. So the end of the definition is here. So a differential operator of order M is clearly a differential operator at most order M is clearly a differential operator of at most order M plus 1. Because we can just choose these functions to be smooth. But, so maybe this is not pedagogically all that good, but coming back into the definition, we can say it is of order M if now D is in diff MEF, but it's not in diff M minus 1 EF. Okay, so it means that somewhere we have to have a non-zero A alpha beta theta in some open set of order M, right? For modulus alpha equal to N. But we'll touch on that a bit later. So this is all this is doing is just really formalizing what we mean by a differential operator of order N. Okay. So just to be succinct, let me instead write du equals alpha equals m a alpha of x d alpha, well, it'll be dk on dx alpha, sorry, dm on dx alpha of u plus lower order terms. So here I want to write, so that the A alpha at x is a fiberwise map defined as, so I mean this is really nothing, this is just unraveling this expression that's written in coordinates. So this is just A alpha of x e beta at x is equal to A alpha theta beta at x of f theta at x. Okay, so the danger with this expression is, I mean, this is really defined with respect to a basis. So I haven't really highlighted that, but so it's sort of sweeping some things under the rug, but we'll see the reason for it in a second. So let's try and understand this top order term here. Okay, so this, in what is to come, this top order term will be of significance. So for the sake of simplicity, let's just restrict ourselves. So for simplicity, restrict to m equal to 1. Okay, so we'll look at the general case in a second, but just to calculate this, let's look at m equals to 1. So let me consider now a map instead, where we are looking at the operator now acting on something sitting in Rn, right? So I want to write d of u composed with psi inverse at x. So this is going to be I equals 1 to n. Now, in the notation that I had before, what I'll have is the AI, because the alpha, the m here is equal to 1, so I'll have the AI composed with psi inverse at x, d on dxi, u composed with psi inverse x, plus this lower order term, which is just going to be a naught at x, u composed with psi inverse x. Okay? So, if we now let v phi be other coordinates near psi of x, right? Okay, so then we can write d of u phi inverse at x. Now with respect to, we can do the same thing and just replace the AI with some BI, right? So let me replace this and write this with the BI. So I'll call the coordinates inside the phi y. Okay, so maybe I'll write y here, sorry. U composed with phi inverse y plus b naught y. Okay. So what do we, let me just draw a quick picture. So what we have here is, we have u, we have v, and we have maps. I hope I've got this the correct way, but I think I have. So I have maps psi and phi. So this is my intersection, and I want to study what happens on this intersection, right? So that's sort of the aim here. So maybe this is my intersection here, and okay, so this is my intersection. So now what I have are coordinates y here, and I have coordinates x here of y, right? So my transformation rule, so going from here to here, I'm going to go via phi, and I'm going to compose, no, that's not the right direction, right? So I'm going this way. So I'm going to compose with phi inverse y composed with psi. Okay, so is this the correct direction? No, I don't think that's the correct direction, sorry. So I want to get from y to x, so x of y, I'm going to have being the y going y. Okay, so I've written this wrong, that's the problem. Sorry, this should be, of course, phi and v, and this should be u and psi. Okay, sorry. So what we have then is we're going to go first via psi composed with phi inverse, and we're going to go to y. So of course I had the arrow correct the first time. Okay, and this is change of coordinates. I'm just writing this very explicitly so that we can just follow through this calculation. So now if I want to change, so if I look at AI composed with psi inverse at x. So this is what, d on dxi, times d on dxi. Of u composed with psi inverse x. So we can write this as equal to a composed with psi inverse composed with psi composed with phi inverse. Sorry, what am I doing here? It's the other way. Just give me 1 second. What am I doing here? Aha. So I want to consider x equals x of y, right? So I'm just trying to make a coordinate transformation. So my y is going to be equal to psi composed with phi inverse. Sorry, my x is equal to this at y. So that's what I'm putting in here. So now I have d on dxi of u composed with psi inverse at psi composed with phi inverse at y. Write it like this. So anyway, the thick and thin of it is, by the chain rule, what we end up with is, maybe you should check this calculation, but in spirit it's correct. D on dyj of u composed with phi inverse of y. Okay, so this is really what I wanted to arrive at. So why do I want to look at this? Well, let me define x. So the notation for this will become clear. So d of 1 at x, and I'm going to define this to be equal to a I theta beta at x tensor d on dx I restricted to x tensor e beta at x tensor f theta at x. So here my e beta at x is the dual bases, the induced dual bases. Namely e beta x eating e alpha x is the Kronecker delta. Okay, so by this calculation, so what this really shows is that this top order this top order object is well defined, and it behaves in a tensorial way, right? So we can see, right, because if we so this transforms in this way, and we can see what it looks like when we require this top order object, and we can try and look at the relationship between these two. And of course, this transformation rule exactly tells us that this top order object is well defined, right? So this is well defined, and it's a smooth section in T star of M tensor E star tensor F. So, I mean, you might object at this stage and say that I've only looked at what happens at the derivative level, because of course this A I theta B also depends on these on these basis vectors for the bundle. But you can see that if we change these basis vectors to something else, the derivative, so we have a derivative here, the derivative will hit the basis vectors and it'll get absorbed into the lower order terms. So the top order term that we're really interested in really behaves nicely. Okay, so it's a globally defined object. So taking inspiration from this first order case, we can now look at, so this is called the principal symbol. So what we've done is we've computed the principal symbol for a first order operator. So taking inspiration from this, let's define the principal symbol when we have a differential operator at most order n. Okay, so let's fix a cotangent vector. So let me fix a cotangent vector. And let me take a function, a smooth function. So, well, maybe there's a connective word here missing. So, and f satisfying what? So I want f at x to be equal to 0, and I want df at x to be equal to psi. Okay? Now fix a v in, say, the fiber E of x. And define the following. So I want to define well, fix this and let v tilde be an extension of v to an open neighborhood of x, and define then the principal symbol. So, well, I won't call it the principal symbol yet. So x psi of v, I'm going to define this. So this is also the mth symbol, right? So for an operator of at most order m, I'm going to call it the mth symbol, v. So in turn, this is defined as follows: 1 on m factorial of the differential operator acting on the nth power of f acting on v tilde. Okay. So this is a global definition, right? So before I did this local calculation, and this is really a global definition. So the first remark is that, of course, this is a section, this is a homomorphism, this is a section of the homomorphism bundle, pullback bundle of E landing us in F, where this pi now, so maybe I should really write pi as more, so maybe I'll just write it here. So this is just for a global description. So this is the foot point map of the cotangent bundle, right? The second remark, so this is remark 1. The second remark is that if this section is 0 for all x, yeah. Well, it's the pullback. Yeah. So so for all x in M and for all psi in T star of M, if this is 0, this is if and only if D is in diff M minus 1 EF. So the definition then is that the principal symbol is the smallest non-zero dm, or I should say dm, when d is in diff m e f. Okay, so I think that works. And you can check that, so this can happen if and only if the alpha, the A alpha, so this can happen if and only if the coefficients that I wrote down in a frame is non-zero in an open neighborhood. Okay. Yes. Well, I mean, this is a vector bundle. The homomorphism bundle is a vector bundle itself. Ah, I see. Yes. That's true. That's true. Yeah. Yeah, so the question was, why am I not writing sections of the homomorphism bundle? That's true. It, you know, maybe strictly speaking, it should be. But, well, these are just technicalities. I'll just leave it up to you to think about it, right? This doesn't really matter so much. I mean, you can write down the object and you can see how it makes sense and the way in which it makes sense. Okay, so, but maybe I should say that, so at the end of the day, you can see that if I fix a point x, a covector psi, this is going to be a map from the fiber E of x to to f of x. Okay, so that's the thick and thin of it. All right. So maybe I'll write an exercise at this moment. So maybe you can verify expression dx equals to ai, what did I write, beta theta x tensor e beta x tensor f theta x when m equals 1. Okay, so I'm really giving you this for arbitrary order operators, but the bulk of this course will be concentrating on first order. Okay, so right. Oh, sorry. Let me just erase this. This is not right. Verify expression. So I'm missing a field here. So the question was, can I explain the definition again? With this definition. So we want to be the principal symbol. This is the smallest non-zero. So this is okay. This is the smallest m. I should write that here. For which this is non-zero with, okay, maybe this is a better way to write it. So remember, if D is diff m e of ef, it's also diff m plus 1 ef. But then this symbol that we write down here will be 0. So I want to look at where this D, all of the diff m's for which this D is in, and then I want to take the smallest m for which this symbol is non-zero. Does that clarify things? Okay. So let me move on. So the first thing I'll ask is, as an exercise, so one can verify this expression for the for order 1, and for order 1 for m equals 1. Another thing you can do, so we asked this, so often, at least the way that I was taught these things, and for order 1, if you want to take things beyond this, no, sorry, the question again was the biggest m. No, it's not the biggest m, because yes, so I want the smallest m. No, I'm asking for D to be in diff MEF. So if I have an operator which is order 1, I cannot have that being in order 0. It's not in diff 0. Or if I have an order 2 operator, if it's in diff 2 EF and the principal symbol is non-zero, or the symbol for m is non-zero for m equals 2, it cannot be in diff 1 MF, because I cannot write it as that expression that I originally defined diff MEF to be. Precisely. And that really is because this set is a filtration. Okay? Okay, so let me come back to this. So again, so what I was saying is that in the non-smooth setting, in the literature, often you see the principal symbol written in a slightly different way, or even the characterization of a first order differential operator in a slightly different way. So and that is, show for m equals to 1 the following: that x psi of v is equal to the commutator. So this is the commutator now. So I multiply by the identity acting on v and x, and this is for f in, say, smooth functions such that df of x is equal to psi, and there's no requirement that f at x is 0, right? So that's the only thing we've dropped. I mean, this is not something really magical, but yeah. So, okay. So these principal symbols compose well. So what do I mean by that? So so I won't really be touching on aspects of symbol calculus too much, but so if D1 is in diff LEF and D2 is in diff MEF, then D1 D2 compose D1 L plus M x psi is precisely equal to just the composition. Try to get that order correct. This is M and this is L x psi. Okay, so I won't prove this, but it comes out of the wash from just the definitions. So a very important class of operators, and basically we're almost exclusively going to be looking at this class of operators, is the following class. So an operator is elliptic if d x psi is invertible for all x in M and for all x, for all psi in T star of M minus 0. Okay. So a simple observation from this, maybe I'll state as an, well, maybe. So simple observation, which you can prove for yourself, is that if D is elliptic, then actually this has a consequence in the underlying bundles, right? So the rank of E has to be equal to the rank of F. I mean, this is just really coming from the invertibility. It's the isomorphism. Okay, so in particular, if I have a invertible, if I have an elliptic differential operator, then it really means that it cannot be diff m minus 1. Okay. So some examples. So the exterior derivative. So this is a very basic map. So these are really non-examples actually, because none of these examples are going to be elliptic. Okay, so this is the exterior derivative. And it's a map that is purely determined by the differential topology of your manifold, right? So there's no geometry in this object. So what is the principal symbol of this? So so this is an order 1 operator. So one can check that. So we take a function which produces psi at x. The differential of that function produces psi at x. So now I'm just going to act on it. I'm going to extend the omega a little bit into a neighborhood. Sorry, that's not definition, that's equal. We've already defined it. And what's this equal to? So this is precisely going to be d f wedge omega at x plus f d omega at x. But we organized f to be 0 at x in the definition, so this thing is 0. F of x is 0. And then the df is precisely psi, right? So this is now going to be psi wedge omega. And omega tilde is an extension of the omega in a neighborhood, so at x it's precisely equal to omega. Okay. So I'll leave it as an exercise, so this is not elliptic. And I'll leave it as an exercise. A second very important example is a connection, right? So this is a map that takes me from CE to here, and it's a connection. So what does that mean? So it satisfies Leibniz rule in particular. If we plug in a vector here, then f of psi is equal to df psi plus f of x psi. So if we compute the principal symbol of this, at x, so this is precisely equal to df tensor v tilde plus f at x. And again, we arrange this thing to be, this term to be 0, right? So f of x, remember, is 0. Therefore, we get that this is exactly equal to psi tensor v. And of course, this is again non-elliptic, right? So it's easy to see this because the rank of E will not be equal to the rank of T star of M tensor E in general. Okay. So I won't give you any examples of elliptic operators just yet because I want to move on to the formal adjoint, and there we will start getting, with that we will start getting some elliptic operators, right? So let E and F, so now I want some Hermitian bundles, okay? So I want a metric structure. So hey, not necessarily a Hermitian structure. So well, let me say, so we're going to continue from the last section. So let H, E, H, F be metrics on E and F respectively. And we fix an mth order operator, so D is in diff M, or at most mth order. Okay. Well, maybe I'll say that it is mth order. So okay. So proposition. So under these conditions, there exists a unique mth order operator that now takes me from C infinity of, so it takes me from F back into E, satisfying the following: that du v L2 mf is equal to u d dagger. So this is not Jesus on the cross, it's a dagger. L2M E now, right? So remember, D maps to F, so we're taking the inner product in F here. And here D maps to E, so we take the inner product in E. And this is for all U in C infinity CC. So these are, remember, sections that do not touch the boundary. And for all V in C infinity CC on F that don't touch the boundary. So let me prove this. Before I prove this, let me just make a remark, right? So the first remark is that D and D perp are automatically densely defined. In L2. That's why I went to the effort of proving this dense definedness in the last section. So this is now bringing us to the functional analysis that we were thinking about earlier, right? Or the functional analysis that we were considering earlier. We automatically have operators, these differential operators are now densely defined in L2. And that's really where we want to consider many of these problems. Okay, so proof. As always, we're going to prove uniqueness first. Suppose that D1 perp and D2 perp satisfy this formula. Okay. So if I look at the difference then, so U D perp 1 minus D2 perp V, everything is nice and linear, so I won't write the inner product here when it's clear, right? So this is going to be D perp, D1 perp V minus U D2 perp V. And this is going to be equal to what? D of UV minus D of UV, so that's 0. Okay, so maybe I didn't need to do that calculation. But remember, every L2 inner product, so this is an L2 inner product, and therefore it's a perfect pairing of L2 with itself, right? That's what a Hilbert inner product is. So, so here we're really looking at L2 of E, right? So L2 of M E, L2 of M E 2K is a perfect pair. So this is a perfect pairing. I could have written this in more succinct notation. So that means that I can write the difference between these two operators, D1 minus D2 of V, as what? So I can write this as, so this is the L2 norm in E. So this is ME. So I can write this as some constant supremum over 0 not U in now L2ME of U D1 perp minus D2 perp V U in L2. Why is it unique? So the question is, aren't we done showing uniqueness? So why is D1 equal to D2? But the difference can be 0 just on some set. I mean, this does not imply that the difference is 0 in L2 or pointwise everywhere. Yes, so you have to prove that it's 0, that it's 0 everywhere from knowing that it's 0 on a certain subset. So what is the device for proving that? Precisely, the operator is not necessarily continuous. So what I want to do is to compute the norm of this thing, but we know that for a perfect pairing we can compute the norm in this way. Of course, the question was right, this is somehow a trivial calculation, but I want to just go through it at least once, so there's an idea of how to use perfect pairings and density to actually obtain such a result, right? So you can replicate also these kind of things beyond the setting here in L2 when you have a perfect pairing. Okay. So now now precisely we can pass to a dense subset. So we know that C infinity CC is dense from the previous proposition. So this is density of C infinity CC in L2. Okay, so now I can pass, instead of looking at U in L2, I can look at non-zero U in C infinity CC M of E. U D1 minus D2 V norm U in L2. And what this precisely means, I mean, we already know this, right? We already wrote this down, and this is exactly so. So this is really for U and V in C infinity CC, or for U in C infinity CC, this formula is true. So this is the remark that I made with perfect pairings. It's very useful when you have nice dense subsets on which you have formulas that you can actually prove, because they're coming from certain classical objects, that you can actually get wider conclusions through going through a perfect pairing. And this is precisely 0. So the norm is 0, and that means that d perp 1 is equal to d perp 2 almost everywhere. Okay, so far we just have this is almost everywhere. So we need to know that these are actually, that the perp object is an object that's defined everywhere. So we're still not done yet, right? So for that, we have to really go through existence. If U is a section with the support of U in big U, where U psi is a chart corresponding to trivializations, corresponding to trivializations. Well, sure, but how do you prove it? So the question is, doesn't this first calculation say it? How do you get from an inner product to a norm? Well, it does. It says it's 0 on a dense subset because of the norm calculation. I mean, we could have a pairing between two spaces, say, and then we might have not be able to do a calculation. I mean, we might be able to verify a certain calculation in a certain way, but if we don't know things like a perfect pairing, I mean, of course, you're right, this does say that the two operators have to be equal, but it says that these two operators are equal because a priori we know that this is a perfect pairing, and because that's the calculation to show that it's 0. Yes, so you're absolutely right. In a Hilbert space, this is true because it's a perfect pairing. But I wanted to really point this out, that the perfect pairing is the key property that comes in, because maybe if you want to replicate such a proof in another setting, where you might not have, I don't know, maybe it's not, maybe it's a Hilbert space, but the pairing is something different, then the calculation that you have to do is a similar calculation, but you have to be careful in the way in which you do it, right? So I'm just really writing it out here for completeness, but of course you're right, it's a trivial thing here. Yes, because there are three criteria for a perfect pairing. The first is that a perfect pairing is bounded above, but the second criteria is that a perfect pairing is bounded below, right? So that was point 2 and 3 for a perfect pairing, and that's precisely what I've used here, right? In this calculation, I'm saying that the norm is bounded above by the supremum of this perfect pair. So that's exactly a non-degeneracy condition for perfect pairings. Yeah. Okay, so let's get back to the existence part. So for the existence part, if we have a chart corresponding to trivializations for E and F respectively, so maybe it's a good idea to fix some notation to say that. So maybe we can say that such a chart is a trivialized chart, or a chart that trivializes EF. Well, we're done with uniqueness that D1 and D2 perp are almost everywhere equal. Precisely. So for that we have to still, so the existence part will give us that. Okay. So we compute this for trivializations, and let's fix some orthonormal frames, right? So let's take the E beta and F theta to be orthonormal. So if that's the case, we can compute this. L2MF. So what's this exactly? This is going to be HF of the sum alpha less than or equal to M A alpha. So remember, in this A alpha, I'm hiding the frames here, right? So everything is orthonormal here. So dx alpha uv. And now I have the density coming out here, and then the Lebesgue measure, right? Or the pullback Lebesgue measure, I should say. So if we expand this out, what we get is we get H, E, U. Now we get 1 on this density alpha less than or equal to M, -1 to the alpha. So I'll leave it up to you to verify this. This is because this is just basically a calculation in Rn. Now we have to insert the density again here, and this is A alpha transpose, and it's the transpose. So this is really where I want to make a point, because we chose our frame to be orthonormal. So I think actually before I was writing the H with a bracket like this, so maybe I'll write that just so everything doesn't get cramped. So this is again with a mu psi d psi pullback d Lebesgue. Okay. Okay, so this is what the expression looks like inside, if the support of U is purely inside a chart. So for a general U, we just do as before, use partition of unity and patch. So the whole point is that when we do this partition of unity and patch, all of the unnecessary terms get absorbed into the lower order parts, right? So derivatives hitting the partition of unity will just become part of the lower order terms. So from that we calculate what this V is. So this is going to be inside this frame, so inside this orthonormal frame, we calculate this to be equal to the transpose dm of dx alpha v plus, now we get lower order terms. So this is, so now, I mean, the A's here were, so the x maps to AX was smooth, or AX alpha, which means that x maps to A alpha X transpose is smooth. And so we can upgrade, so that means we can upgrade the D alpha 1 equals D alpha 2 almost everywhere to everywhere. Okay, so that finishes existence and uniqueness in both parts. So if you look in many places, actually there wouldn't be an argument for the uniqueness in terms of, as we did here, in terms of the perfect pair, but I really just wanted to do it just to take you through a calculation with the perfect pairing. Okay. Precisely, that's what I mean. Yes. Yeah. So the question was, does almost everywhere mean apply to functions? It's almost equal almost everywhere. That's really what I mean, right? So so I should maybe write this. Okay, thank you. Anyway, that's just a technical thing. So so more or less, it is what you expect it to be. So you can also see that it's kind of funny that the formal adjoint actually doesn't contain any information regarding the measure or the density. I mean, here in the transpose, we do use the fact that H is that we've written everything out in an orthonormal frame, but you know, the derivatives hitting the measure or the alpha, this gets absorbed into the lower order terms, right? And so everything cancels. So the formal adjoint is somehow more, it's a more intrinsic object in some sense. Okay. So okay, so I've maybe I don't know if I wrote this down here, that this is called the formal adjoint. Okay, so I didn't define it. Sorry. So this is what we call the formal adjoint. Okay, so definition. For D in diff MEF nth order, the unique D perp in, or D dagger, sorry, diff MFE is called the formal. So the formal adjoint doesn't see things like what happens on the boundary. Okay, so, but it tells us that D is adjointed. So there is a non-empty adjoint for D. So it could be that if you fix an operator, of course you always get an adjoint. I mean the adjoint, as we talked about before, because these spaces are reflexive. But there's no guarantee that this adjoint is going to be non-zero. But here we can see that the adjoint is a maximal object, so it certainly contains a non-zero object, right? So we really have non-trivial objects here, and somehow in smooth geometry, C infinity CC is the key. It's the king, and that sits at the heart. It's really the core of all of the. Or I shouldn't call it the core because core has a meaning. It's really at the heart of all of these operators. So let me now also make a quick remark that allows us to calculate things, and I'll of course not prove this again. So if D is in diff MEF, then the so maybe I won't have, I don't know, this is -1 x psi bar. So here again I'm using the dagger notation to denote the fiberwise adjoint. Okay, so maybe that's something to keep in mind. So you might, okay, sorry, there's an order M here. So you might think that this is a bit odd. So in many situations that we'll look at, or in many situations in geometry, you often have that E is equal to F, and actually D is equal to D perp. Right? This arises in many situations. And further, when m is equal to 1, we have something weird here, right? So we have that the formal adjoint, which is, as I said, equal to itself, is now minus more or less the transpose of itself. So what it's saying is that the symbol, the principal symbol, is skew adjoint. So for formal adjoint things, we have something skew adjoint. And that looks a bit strange because you would maybe want that for formally adjoint things, you want the symbol to also be symmetric, right? This is saying it's skew symmetric. And there's a good reason for this, because we want, so this really comes down to the fact that we want consistency when the field is real. So let's look at it explicitly. So I should say i.e. dx psi is skew adjoint from the point of view of matrices. So the point here is that this is for consistency. So this is for consistency with the reals. So, I mean, let's take the operator that we know and love, one-dimensional analysis, d on dx uv is equal to u negative d on dxv, right? This is what we know, and this is for real valued things. And so what is the principal symbol of d on dx? Well, here the principal symbol is just x. I mean, it's just a real number. Sorry, it's just psi itself, right? That's the principal symbol. So in this situation, we see that for the formal adjoint, we require this negative condition because we don't have. I mean, if we were working on the complex numbers, we could consider I d on dx. And this is now a self-adjoint operator which is complex valued, and in that case we see that everything matches up, right? So the reason that we really consider the skew adjoint case is so that everything matches up when we have the field being real. Okay, so the point is we cannot consider that object, right? This skew symmetric condition, right? Because in the so here we have only skew symmetric. So here we have a formal adjoint which can only be skew symmetric because we don't have complex numbers to play with if the field is real. And in that case, we have that the symbol of the adjoint is itself. So we only have, so the formal adjoint here is negative of d on dx. Maybe I'll write it out. So if I write, so we only have one object here, which is d on dx, perp, and this here is going to be equal to negative d on dx, xi. And so what we have here is that this is equal to negative 1 to the power of m, right? So of d on dx xi transpose, and then this is equal to negative psi. So it agrees with the formal adjoint in the it agrees with the formal adjoint in the real case. Anyway, let's not dwell on this too much. This is just a side remark. So you can try your hand at this calculation if you like, just to verify things. So let's have a look at a couple of examples. So fix G to be a Riemannian metric on M, and define the cut product. So I noticed that some people write this the other way, and I actually don't know what this notation is. I learned this from Leon Simon's book on GMT. So this is the adjoint. So the cut product here is the adjoint. So so the way I always remembered it is that psi is cutting into eta. So so we define this way, and let d dagger g denote formal adjoint. Okay. Yeah, so it's the interior product or the cut product, depending on which way you want to think about it. You can write it. So anyway, so this is a so I should say that this is okay. So so this is diff 1 of the bundle exterior derivative. So this is the formal adjoint of D. So x psi is equal to psi cut omega. Okay. So I won't verify these things too much. So the Laplacian now. So what is the Laplacian? So the way I define the Laplacian is the interior product, sorry, the formal adjoint acting on the exterior derivative. So you would see that this is also written as div composed with grad, or negative div composed with grad in books. I don't like this. So this is the Laplace Beltrami, right? Let me say what this is first. So this is the Laplace Beltrami operator on M. So I don't like this div grad notation, because when you take the gradient, then you're really taking D and you're lifting it through a musical isomorphism to vector fields. So the gradient is an operator that acts on vector fields. And the reason I don't like this is because it mixes up the topology and the geometry. So here, the exterior derivative is purely determined by the topology, and then this d dagger g is the thing that encodes the geometry. And one can show that this is exactly equal. If you go through the musical isomorphisms and everything, this is exactly equal to what people call div composed with grad. So what is the symbol of this? So if we just use this compositional, if we use the compositional formula for the adjoint, it's easy to see that this is going to be positive operator, which is just the absolute value of the covector, and this one can just do by looking at what happens if you first wedge and then cut. Okay. And this is in fact, so one can see that this is in fact an elliptic operator. Because for non-zero psi, this is invertible, right? This principal symbol is invertible. So we've met our first elliptic operator. The other important operator is d plus dg dagger. So this is again a diff op. This is a differential operator of order 1 on the exterior bundle. And this is the Hodge-Dirac, or at least I know it as the Hodge-Dirac. And so the principal symbol here. So the happy story about first order operators is that it's linear in the psi variable, right? So the principal symbol of this is easily checked to be that. And this is also elliptic. So this is an elliptic second order operator. And this is elliptic first order. Yes? Yeah. Yes, there's normally a minus. So the question is, why isn't there a minus sign in the Laplace Beltrami? Let me think. So why am I not getting a minus sign here? If I take... Maybe I'm contradicting what I said before with the symbol of let me just think. So here we have to have that, so this is going to be dg perp x psi composed with d of x psi, and we know that the formal adjoint, so this is going to be negative dx psi composed with dx psi. Yes, so we wedge and insert, so and the d of x psi, so this is going to be psi wedge, and then this is again negative wedge. Okay, it's up to, I can't compute these things on the fly, so this is plus or minus depending on convention, right? So chase this up, so calculate it, and then you can maybe see what it should be. So change style, so let's do that. So check, I'll leave this to as a check. If I try and do it now, I'm very slow calculating things, so it would take me a while to figure all of this out under pressure. So check. So it's either plus or either minus. In either case, it's invertible. Okay, so it's a reasonable thing to try and compute. So it's going to be minus 1 of this. Yeah, so it could be that there is a minus sign on there, and I could have gotten that wrong. Okay, so sorry about that. There will be mistakes, and if you see mistakes in the lecture notes, please forward them on to me so that it's fixed up in the final version. Okay, so we have 10 minutes to go, and maybe in those 10 minutes we can just start with some motivation. So now that we've talked about formal adjoints and various other things, what we really want to do is to start talking about boundary value problems. And I was hoping to move on to that today, but it looks like it'll be next time when we do it. But let's just restrict ourselves to the case of motivation for maximal and minimal extensions. So I think I can do this in the 10 minutes. So let's consider a very, very, very particular situation. So let's consider partial j, which is equal to partial on partial xj, and let's consider this on a smooth bounded domain. So smooth let's say bounded domain in R, I don't know why I call it DRN. So what do we know? So what I really want to talk about is something you already know. You've seen weak derivatives, you've seen distributional derivatives, but I want to talk about that in the context of of operator theory, right? I want to see it from an operator theoretic point of view to set us up for what should happen later. So let U and V be compactly supported functions. So, I mean, we know for such functions we have that the partial derivative of U d Lebesgue is equal to negative U partial derivative V d Lebesgue. Okay. In other words, so let's write this out as inner product. So dj of uv is equal to, and I'm going to put the negative sign on the operator here, on this side, right? Because of course the negative partial j is the formal adjoint of partial j, right? That's what it's really saying. So recall what it means when we talk about the distributional derivative. So recall distributional derivative. So what we want to do is we want to define for U in L2, we want to define so we want to extend, so we want to define partial j, I'll call it lowercase dist for distributional. And I want it to go from L2 of omega to C infinity CC star. So these are going to be my, or I'll maybe write dual here. So this is just, I mean, I'm not going to talk about a topology on here. I just want this to be a C linear functional. On C infinity CC. So how would I define this? Well, the point is really to be inspired by this formula, right? It's really to be inspired by the adjoint formula. This is really at the heart of it. So I define dj dist acting on some function v. So I want it to also agree with what happens when I have something that's compactly supported smooth. So the only way I can really do that is if I define it to be as follows. Okay, so this is going to take some function v, and it's going to produce me a real number. This is now functional on compactly supported smooth functions. So connected with that, we also have the notion of a weak derivative. So remember that a weak derivative is if we say that there is some L2 function such that, so again, I'll write this just to familiarize ourselves, or just to think in terms of these inner products. So we say that f is a weak derivative if, I mean, it's typically, when you learn these things, it's only the formula in the middle that's written down, right? So this is equal to f v bar, and this is saying that, so it's really this part that's really written down in books when you study this. So the definition of the no, the left hand, sorry, here, sorry, dj sorry, I thought you meant somewhere else. U acting on V. That's correct. Sorry about that. Okay, so the definition now of the weak derivative of this U is this F. Okay, and so again, because of these dense considerations of compactly supported functions in L2, we can see that this is a unique map. So what are such F? So clearly, if F is in L2 satisfying this, we have that U partial JV is equal to FV, and by the Cauchy-Schwarz, well, it's not, by the Cauchy-Schwarz inequality, this is going to be F in L2 and V in norm, right? So this is just Cauchy-Schwarz. Okay. And the point is that this is for all V in C infinity CC, which is dense in L2, right? So this is satisfied for all V in a dense subset. So conversely, suppose that U partial J V is bounded by some constant, possibly depending on U, against V in L2 for all V in C infinity CC of omega. So by the Riesz representation theorem, we have a unique F in L2 such that U negative partial JV is precisely equal to this FV. Okay, but what is this? So what is this set? So we've now characterized the set of all such F such that this can happen, right? So so what is this set exactly? Well, consider, so we consider partial J of C to be equal to, so let the operator partial J of C act as partial J with domain dom partial J of C, well, equal to compactly supported smooth sections. Sorry, I'm going a little bit over time, but I'll be done very soon. So if we take this as the operator with domain, so what is now the domain of partial J C adjoint? So this is the adjoint, right? So this is the maximal object. So this is going to be all the U in L2 such that there exists an F in L2 such that for so that for all V in C infinity CC we have that U negative partial J, sorry, I should put a negative sign here, CV is equal to FV, so I should maybe put the negative here, okay, of course the negatives cancel, but anyway, just for completeness let me put it. So this is exactly the set that we characterize, right? So we can also write this, so this is exactly this set that we wrote up before. So the weak derivative is actually the adjoint of the operator negative partial JC with this domain. Okay, that's precisely the weak derivative. And we can also characterize this in terms of the distributional derivative. So this is saying this is the U in L2 such that the partial J distributional of U is again in L2. Typically, it's not going to be in L2, it's just a functional. But now we want it to be an actual object in L2. So what does this mean? So the second line here, so if I have a distribution, so this is a this is a dual map, we say that this is in L2 if T of U can be represented by some F, right? So if there exists some unique TF in L2 such that T of some V is equal to TFV, right? So this is what it means. So anyway, the thick and thin of it is that is the real take-home message is this, that the partial J that you've seen before, the weak derivative that you have seen before, is actually exactly equal to the adjoint, the L2 adjoint of the operator partial JC, which is negative partial JC, which is the operator defined on compactly supported smooth functions, right? So I want to end it here because from next time onwards, we will replace these partial J's with the operators that we want to study, because this now gives us an operator theoretic route to thinking about. So this is a rephrasing of weak derivatives, distributional derivatives, and all of this sorts of stuff in terms of operator theory. And in this more general context, what we have is the operator theory. So this is the approach we'll take from the next session onwards in defining the various operators that we get before we can start talking about boundary value problems. Okay, thank you very much. I'm sorry for going over time. Yeah, I'll end it here. Very quickly. So I'll stop the record. Oh, okay. Are there any questions? Maybe I should very quickly say that that the question before was correct. So this should really be negative, right? Because if for the Laplacian, the formal adjoint of the Laplacian is so the symbol should be skew symmetric. So skew symmetric in particular should mean that yes, I think there should be a negative sign in front, but maybe you can calculate that and explicitly follow up this thing. Yeah. Well, I mean, the thing is that this is now the formal adjoint of the Laplacian is itself. So if I now take the formal adjoint and it is itself, then we have so we have this relationship here, that the formal adjoint should be negative of the symbol of the adjoint transposed. Yes, so but this is of order n. Oh, it's of order 2. Aha, you're absolutely right. So I screwed that up. Yes, the minus sign doesn't change anything. It's worthwhile chasing it up. So I prefer to have positive operators. So actually, I think it was correct the way that I had it, that it should be a plus sign here and not a minus sign. And the real difference comes in whether you write the Laplacian as div grad or negative div grad. No, I think it should be the other way around, because div is typically div is negative of the adjoint. So for me, so at the end of the day, I want positive operators. Yeah, it's only convention, but at the end of the day, I want positive operators, right? I'm a positive guy, so I want my Laplacians to be positive. Yeah. Yeah, all of this language goes back to this language of whether you want accretive or dissipative operators. So if you read, for instance, Cato, he talks about dissipative operators and accretive operators, and you know, he naturally people have considered these operators where things are sitting on the negative spectral side, and then they multiply by a negative so that everything sits on the positive side, and then they do stuff. But for me, you know, I want my second order operators, I want them to be positive from a spectral point of view. So it is convention, but of course I fixed the convention here, right? In when I've written this, when I've written the definition of the adjoint. So well, it's maybe worthwhile chasing it up and figuring out what it should be. But for the purposes of, so you might say, why am I not caring about this at all and just sweeping it under the rug? The point is that when we're looking at first order operators, necessarily first order differential operators will have spectrum on both sides. So because they're going to have spectrum on both sides, because see, for a first order operator, the map psi mapping to the symbol x psi is a linear map. So you're going to have the symbol being on basically both sides, right? So if I multiply psi by negative psi, I'm going to have the symbol swapping over. And so, and I'm really a first order boy. So I've never really cared about the conventions of the symbol, except that I want my second order operators to be positive. That's the short answer of why I'm careless. Mm-hmm. Yes. Yes. Yes, that's right. Yes. Yes. Okay, so I think from next time we will get on to the real thrust of all of this. So we'll start with, you know, considering these distributional things and weak things in terms of operator theory. So, okay. So the course really starts from the next lecture. Okay, thank you. Right, I'll do that right now. And I'll stop recording.